Are we shadows dancing in a grand, unseen ballroom? Exploring the whispers of extra dimensions. The universe, as we perceive it, is a vast and awe-inspiring canvas painted with stars, galaxies, and the intricate dance of fundamental particles. We navigate this canvas with our three spatial dimensions, length, width, and height, and track its unfolding story through the dimension of time. This 3+1 dimensional picture, meticulously crafted by centuries of scientific inquiry, has served us remarkably well. It allows us to build bridges, launch rockets, and understand the subtle nuances of the subatomic world. But what if this familiar portrait is incomplete? What if our universe is not merely a 3+1 dimensional entity, but a far more complex and enigmatic reality, shimmering with hidden dimensions that we can barely glimpse? This is not the stuff of science fiction, but a profound question that has captivated physicists and mathematicians for over a century. The idea of extra dimensions, far from being a whimsical fantasy, arises from some of the deepest and most perplexing problems in modern physics, offering tantalizing hints of a universe far grander and stranger than we can currently imagine. Let's embark on a journey, then, into the realm of the unseen, a quest to unravel the mysteries whispered by the mathematics of extra dimensions. We'll delve into the motivations for their existence, explore the various theoretical frameworks that embrace them, and ponder the profound implications these hidden realms might have for our understanding of the universe, its fundamental forces, and even our own existence. Fasten your seatbelts, for this is a journey that will challenge your perceptions and expand your horizons. 1. The shadows in Plato's cave. Why we need extra dimensions. To understand the allure of extra dimensions, we must first grapple with the limitations of our current understanding of physics. Our most successful theories, general relativity, describing gravity and the large-scale structure of the universe, and quantum mechanics, describing the behavior of particles at the subatomic level, are incredibly accurate within their respective domains. However, when we attempt to reconcile these two pillars of modern physics, cracks begin to appear in the foundations. A, the gravity-Gordian knot, the hierarchy problem, and the weakness of gravity. One of the most glaring discrepancies arises from the vast difference in strength between gravity and the other fundamental forces, the electromagnetic force, the weak nuclear force, and the strong nuclear force. Gravity, the force that governs the celestial dance of galaxies, is staggeringly weak compared to the forces that bind atoms together. To put it into perspective, a simple refrigerator magnet can easily overcome the gravitational pull of the entire Earth to hold itself in place. This disparity, known as the hierarchy problem, is not merely an aesthetic issue. It points to a deeper, more fundamental puzzle. The standard model of particle physics, our best description of the fundamental particles and forces, requires incredibly precise fine-tuning of parameters to maintain this vast difference in strength. Imagine adjusting 1,000 knobs on a machine with unfathomable precision to achieve a specific outcome. It seems highly improbable, bordering on absurd. Extra dimensions offer a potential solution to this riddle. The underlying idea is that gravity, unlike the other forces, might not be confined to our three spatial dimensions. Instead, it could be diluted by spreading out into these extra dimensions. Imagine a water hose. If you concentrate the water flow at the end of the hose, representing our 3D space, the pressure is high. But if you allow the water to spread out into a larger container, representing extra dimensions, the pressure at any given point is significantly reduced. In this scenario, the gravity we experience in our 3D world is merely a fraction of its true strength. Its intrinsic strength could be comparable to the other forces, but its effect is diminished by its leakage into the hidden dimensions. This eliminates the need for fine-tuning and provides a more natural explanation for gravity's apparent weakness. B. The quest for unification, towards a theory of everything. Another compelling motivation for exploring extra dimensions stems from the long-standing quest to unify all the fundamental forces into a single, elegant theory. Physicists have dreamt of a theory of everything that would seamlessly weave together gravity, electromagnetism, and the nuclear forces into a cohesive and complete description of the universe. Einstein himself spent the latter part of his life pursuing this dream, but he ultimately failed. The problem, in essence, is that general relativity and quantum mechanics speak different languages. General relativity describes gravity as a curvature of space-time, a smooth and continuous fabric. Quantum mechanics, on the other hand, describes the other forces as mediated by discrete particles, acting within a probabilistic framework. Extra dimensions offer a potential bridge between these seemingly disparate realms. By adding more dimensions to the space-time arena, we can potentially embed the different forces within a single, higher-dimensional geometric structure. Imagine drawing two lines on a flat piece of paper. They appear distinct, but if you roll the paper into a cylinder, the lines can become part of a single, continuous spiral. Similarly, the different forces we observe in our 3D world could be different manifestations of a single, unified force in a higher dimensional space. This unified force, acting within the extra dimensions, would then manifest as the distinct forces we observe in our familiar reality. See The Ghost in the Machine, Fermion generations, and the mystery of mass. The standard model of particle physics, despite its remarkable success, also leaves several unanswered questions. One such question revolves around the existence of three generations of fundamental fermions, quarks and leptons. These generations are essentially copies of each other, differing only in their masses. Why do we have three generations? What determines their masses? The standard model provides no satisfactory answer to these questions. It simply accepts the existence of these generations as a given, plugging their masses into the equations without explanation. Extra dimensions offer a potential avenue for addressing this puzzle. The idea is that the different generations of fermions might arise from the different ways particles can propagate through the extra dimensions. Imagine a vibrating string fixed at both ends. It can vibrate in different modes, each with a different frequency and wavelength. Similarly, particles propagating through extra dimensions can exist in different modes, each with a different energy and, consequently, a different mass. These different modes could then correspond to the different generations of fermions. The precise geometry of the extra dimensions would then determine the masses of these particles, providing a potential explanation for the observed mass hierarchy. D. The enigma of dark matter and dark energy. Unseen influences on the cosmos. Our understanding of the universe is further complicated by the presence of dark matter and dark energy, two mysterious entities that make up the vast majority of the universe's mass energy content. Dark matter, as its name suggests, does not interact with light, making it invisible to our telescopes. Its presence is inferred from its gravitational effects on visible matter, such as the rotation of galaxies and the bending of light around massive objects. Dark energy, even more enigmatic, is a repulsive force that is causing the universe to expand at an accelerating rate. Its nature is completely unknown, and it accounts for roughly 68% of the universe's total energy density. While extra dimensions are not necessarily a direct explanation for dark matter or dark energy, they could provide a framework for understanding their nature. For instance, some models propose that dark matter particles might reside primarily in the extra dimensions, interacting only weakly with particles in our 3D world. This would explain why they are so difficult to detect. Similarly, the geometry of the extra dimensions could influence the expansion of the universe, potentially contributing to the observed dark energy effect. While these are speculative ideas, they highlight the potential of extra dimensions to shed light on some of the most perplexing mysteries of the cosmos. 2. The landscape of possibilities, exploring different models of extra dimensions. The idea of extra dimensions is not a single monolithic theory. Instead, it encompasses a diverse landscape of theoretical models, each with its own unique features and predictions. These models can be broadly categorized into two main types: compactified extra dimensions and large extra dimensions. Kaluza-Klein theory, the genesis of extra dimensions. The earliest attempt to incorporate extra dimensions into physics dates back to the 1920s, with the work of Theodore Kaluza and Oscar Klein. Their theory, known as Kaluza-Klein theory, proposed the existence of a single extra spatial dimension curled up into a tiny circle. The ingenious idea behind Kaluza-Klein theory was that this extra dimension could be used to unify gravity and electromagnetism. By extending Einstein's theory of general relativity to 5 dimensions, 4 spatial dimensions plus time, Kaluza and Klein found that the equations naturally split into 2 sets, one describing gravity in 4 dimensions, and the other describing electromagnetism. In essence, electromagnetism was seen as a manifestation of gravity in the extra dimension. The photon, the particle that mediates the electromagnetic force, was interpreted as a vibration in this curled-up dimension. While Kaluza-Klein theory was a bold and insightful attempt at unification, it ultimately fell short. It failed to incorporate the weak and strong nuclear forces, and it struggled to explain the observed properties of elementary particles. However, it laid the groundwork for future explorations of extra dimensions, and its core ideas continue to resonate in modern theoretical physics. String theory, the symphony of vibrating strings in higher dimensions. String theory, arguably the most ambitious and comprehensive attempt to unify all the fundamental forces, postulates that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings, far smaller than even atoms, vibrate in different modes, each corresponding to a different particle with a different mass and charge. One of the most remarkable features of string theory is that it requires extra dimensions for its mathematical consistency. In its original formulation, known as bosonic string theory, it required 26 dimensions. Later, with the incorporation of supersymmetry, a symmetry relating bosons and fermions, the required number of dimensions dropped to 10. These extra dimensions are typically assumed to be curled up into tiny, compact spaces, far too small to be directly observed. The precise geometry of these compactified dimensions, known as Kaluza-Klein manifolds, plays a crucial role in determining the properties of the particles and forces we observe in our 3D world. String theory offers a potentially elegant solution to the problem of quantum gravity. By replacing point-like particles with extended strings, it avoids the singularities and infinities that plague conventional quantum field theory. It also provides a framework for incorporating all the fundamental forces into a single, unified theory. However, string theory is not without its challenges. It is notoriously difficult to test experimentally due to the incredibly small size of the strings and the high energies required to probe them. Furthermore, the vast landscape of possible Kaluza-Klein manifolds leads to a seemingly infinite number of possible universes, making it difficult to make specific predictions. M-theory, the mother of all string theories. In the mid-1990s, a revolution occurred in string theory with the realization that the different versions of string theory were not independent theories, but rather different aspects of a single, underlying theory known as M-theory. M-theory, whose precise nature is still not fully understood, is believed to live in 11 dimensions. It incorporates not only strings, but also higher dimensional objects called branes. Branes can be thought of as membranes or surfaces that can exist in various dimensions. M-theory provides a framework for unifying the different string theories, as well as a theory called supergravity, which describes gravity in the presence of supersymmetry. It is considered by many to be the most promising candidate for a theory of everything, although it remains highly speculative. Deep, large extra dimensions, a new twist on an old idea. While string theory and M-theory typically involve compactified extra dimensions that are far too small to be directly observed, another class of models proposes the existence of large extra dimensions that could potentially be detected in experiments. These models, pioneered by Nima Arkani-Hamed, Savas Dimopoulos, and Jihad Valley, ADD, suggest that gravity might be weak because it is diluted by spreading out into these large extra dimensions. The other forces, on the other hand, are confined to our 3D world. In the ADD model, the size of the extra dimensions could be as large as a millimeter, which is enormous compared to the Planck length, the fundamental scale of quantum gravity. This opens up the possibility of detecting the effects of these extra dimensions in high-energy particle colliders, such as the Large Hadron Collider, LHC, at CERN. One potential signature of large extra dimensions would be the production of gravitons, the particles that mediate gravity, that escape into the extra dimensions, leading to a missing energy signal in the detector. Another possibility is the production of microscopic black holes, which would rapidly decay into a shower of particles. While the LHC has not yet found definitive evidence for large extra dimensions, it has placed constraints on their size and properties. The search for these hidden dimensions continues, and future experiments may yet reveal their existence. Warped extra dimensions, Randall-Sundrum models, and the curvature of spacetime. Another intriguing class of models, proposed by Lisa Randall and Randall-Sundrum, involves warped extra dimensions. In these models, the extra dimension is not simply a flat, compact space, but rather a curved space with a specific geometry. The Randall-Sundrum, RS, models provide an alternative solution to the hierarchy problem. In the original RS-1 model, our 3D world is located on a membrane, embedded in a 5-dimensional spacetime with a warped geometry. The warping of spacetime creates an exponential hierarchy between the Planck scale, the fundamental scale of gravity, and the electroweak scale, the scale of the weak nuclear force. This allows for a natural explanation for the weakness of gravity, without requiring fine-tuning of parameters. The RS models also predict the existence of new particles, such as Kaluza-Klein gravitons, which could potentially be detected at the LHC. 3. The experimental quest, searching for evidence of extra dimensions. The theoretical appeal of extra dimensions is undeniable, but the ultimate test of any scientific theory is its ability to make predictions that can be verified by experiment. The search for experimental evidence of extra dimensions is a challenging but crucial endeavor, pushing the boundaries of our technological capabilities and scientific understanding. High-energy colliders, smashed atoms, and the echoes of hidden realms. High-energy particle colliders, such as the Large Hadron Collider, LHC, at CERN, are powerful tools for probing the fundamental structure of matter and spacetime. By smashing particles together at incredibly high energies, physicists can create new particles and explore the interactions between them. The LHC has been instrumental in testing the standard model of particle physics, and it has also been used to search for evidence of extra dimensions. As mentioned earlier, one potential signature of extra dimensions would be the production of gravitons that escape into the extra dimensions, leading to a missing energy signal in the detector. Another possibility is the production of Kaluza-Klein particles, which are heavier versions of the known particles that arise from the compactification of extra dimensions. These particles would have specific masses and decay patterns, which could be used to identify them in the detector. The LHC has not yet found definitive evidence for extra dimensions, but it has placed constraints on their size and properties. The search continues, and future upgrades to the LHC, as well as the development of new particle colliders, may yet reveal their existence. Beach gravity experiments, probing the subtle dance of gravity at short distances. Another approach to searching for extra dimensions is to perform precision measurements of gravity at short distances. If extra dimensions exist, they could modify the way gravity behaves at small scales, potentially leading to deviations from Newton's law of gravity. Experiments that measure the gravitational force between small objects at distances of less than a millimeter are particularly sensitive to the effects of large extra dimensions. These experiments have placed constraints on the size of the extra dimensions, ruling out the possibility that they are as large as a millimeter. However, there is still room for extra dimensions to exist at smaller scales, and future experiments with improved sensitivity could potentially detect them. These experiments are challenging as they require extremely precise measurements of very weak forces. C's cosmological observations, peering into the early universe for clues. The early universe, a time of extreme temperatures and densities, may have been a more hospitable environment for extra dimensions. The geometry of the extra dimensions could have influenced the expansion of the universe, leaving imprints on the cosmic microwave background, CMB, the afterglow of the Big Bang. Precision measurements of the CMB, such as those made by the Planck satellite, can be used to search for these imprints. The presence of extra dimensions could also affect the production of primordial black holes, which could then evaporate and leave behind observable signatures. Cosmological observations provide a complementary approach to searching for extra dimensions, offering a window into the universe's earliest moments. D. Neutrino physics, unraveling the secrets of the ghostly particles. Neutrinos, the elusive and nearly massless particles, may also provide clues about the existence of extra dimensions. Neutrinos are known to oscillate between different flavors: electron neutrino, muon neutrino, and tau neutrino, a phenomenon that requires them to have mass. The origin of neutrino masses is still a mystery, and some models propose that they arise from interactions with particles in the extra dimensions. These models predict the existence of sterile neutrinos, which are neutrinos that do not interact with the weak force. The search for sterile neutrinos is an active area of research, and their discovery would provide strong evidence for the existence of extra dimensions. 4. The philosophical implications. A universe beyond our comprehension? The existence of extra dimensions, if confirmed, would have profound implications for our understanding of the universe and our place within it. It would challenge our intuitive notions of space and time, and it would force us to reconsider the fundamental laws of physics. A. The anthropic principle. Are we living in a special universe? The anthropic principle suggests that the laws of physics and the constants of nature are fine-tuned for the existence of life. If the fundamental constants were even slightly different, the universe would be inhospitable to life as we know it. The existence of extra dimensions raises questions about the anthropic principle. If there are many possible geometries for the extra dimensions, each corresponding to a different set of physical laws, then why do we live in a universe with a particular geometry that allows for life? One possibility is that our universe is just one of many universes in a multiverse, each with its own set of physical laws. We happen to live in a universe that is conducive to life, while other universes are barren and lifeless. B. The nature of reality. What is real? The existence of extra dimensions also raises questions about the nature of reality. If there are hidden dimensions that we cannot directly perceive, then what does it mean to say that something is real? Are these extra dimensions simply mathematical constructs, or do they have a physical existence? Are they accessible to other forms of life, or are they forever beyond our reach? These are deep philosophical questions that have no easy answers. The exploration of extra dimensions forces us to confront the limits of our knowledge and to question our assumptions about the nature of reality. C. The future of physics, a new paradigm? The search for extra dimensions is a testament to the power of human curiosity and the relentless pursuit of knowledge. It represents a bold attempt to unravel the mysteries of the universe and to construct a more complete and unified picture of reality. Whether or not extra dimensions are ultimately confirmed, the quest to understand them has already led to significant advances in theoretical physics and experimental technology. It has pushed us to think outside the box and to explore new possibilities. The discovery of extra dimensions would undoubtedly revolutionize physics, ushering in a new paradigm that would transform our understanding of the universe. It would open up new avenues of research and lead to new technological breakthroughs. Even if extra dimensions remain elusive, the journey to find them will continue to inspire and challenge us for generations to come. The universe is full of mysteries, and the pursuit of knowledge is a never-ending quest. 5. A glimpse beyond the veil, speculative implications, and the realm of imagination. While the primary focus of the search for extra dimensions lies firmly within the realm of scientific inquiry, it's impossible to resist venturing into the realm of speculation and imagination. What might the discovery of extra dimensions unlock in terms of technological possibilities and our understanding of the cosmos? A. Interdimensional travel, a distant dream or a future reality. The concept of traveling through extra dimensions has long been a staple of science fiction. Could the existence of these hidden realms one day allow us to bypass the limitations of our three-dimensional space and travel vast distances across the universe in the blink of an eye? While the idea of interdimensional travel remains highly speculative, it's not entirely the realm of possibility. If we could somehow manipulate the geometry of space-time and create wormholes or shortcuts through the extra dimensions, it might be possible to traverse interstellar or even intergalactic distances much faster than we can currently imagine. However, the energy requirements for such feats would be astronomical, and we currently have no idea how to manipulate space-time in such a way. Interdimensional travel remains firmly in the realm of science fiction for now, but the possibility, however remote, is tantalizing. B. Accessing new energy sources, tapping into the quantum vacuum. The existence of extra dimensions could also open up new possibilities for harnessing energy. Some theories suggest that the extra dimensions are filled with a vast reservoir of energy known as the quantum vacuum energy. If we could find a way to tap into this energy source, it could revolutionize our energy production and solve many of the environmental problems we face today. However, extracting energy from the quantum vacuum is a notoriously difficult task, and it remains a major challenge for physicists and engineers. C. Unveiling the secrets of consciousness, a deeper connection to reality. The relationship between consciousness and the physical world is one of the deepest and most enduring mysteries of philosophy and science. Could the existence of extra dimensions shed light on this mystery? Some speculative theories propose that consciousness might be linked to the quantum realm and that it might even be able to access information from other dimensions. While these ideas are highly controversial and lack empirical support, they highlight the potential for extra dimensions to challenge our understanding of the nature of consciousness and its place in the universe. D. Understanding the origin of the universe, a multidimensional genesis. The Big Bang Theory describes the universe as originating from an extremely hot and dense state. However, it doesn't explain what caused the Big Bang or what existed before it. The existence of extra dimensions could provide a framework for understanding the origin of the universe. Some theories suggest that the Big Bang was caused by the collision of two brains in a higher dimensional space. This brain collision could have released a tremendous amount of energy, triggering the expansion of the universe and the creation of matter and energy. While these ideas are speculative, they offer a tantalizing glimpse into the possible origins of our universe and the role that extra dimensions might have played in its creation. 6. The unfolding tapestry, the future of extra-dimensional research. The search for extra dimensions is an ongoing quest, a journey into the unknown that will continue to challenge and inspire us for years to come. What does the future hold for this exciting field of research? A. The next generation of experiments, pushing the boundaries of technology. The next generation of particle colliders, such as the Future Circular Collider, FCC, will have even higher energies and luminosities than the LHC, allowing physicists to probe the fundamental structure of matter and space-time with unprecedented precision. These experiments will be crucial for searching for evidence of extra dimensions and for testing the predictions of various theoretical models. In addition, new gravity experiments with improved sensitivity will be needed to measure the gravitational force at even shorter distances. B. Theoretical developments, refining our models and exploring new possibilities. Theoretical physicists will continue to refine existing models of extra dimensions and to explore new possibilities. This will involve developing more sophisticated mathematical tools and techniques, as well as incorporating new insights from other areas of physics, such as cosmology and string theory. C's interdisciplinary collaboration, bridging the gap between theory and experiment. The search for extra dimensions requires a close collaboration between theoretical physicists, experimental physicists, and mathematicians. This interdisciplinary collaboration is essential for developing realistic models of extra dimensions and for designing experiments that can test these models. D. Public engagement, sharing the wonder and excitement of scientific discovery. It is important to engage the public in the search for extra dimensions and to share the wonder and excitement of scientific discovery. This can be done through public lectures, science museums, and online resources. The search for extra dimensions is a testament to the power of human curiosity and the relentless pursuit of knowledge. It is a journey that will continue to challenge and inspire us for generations to come. 7. Beyond the dimensions, a universe of unending mystery. The exploration of extra dimensions is not merely a scientific endeavor. It is a philosophical and even spiritual quest. It is a search for meaning and understanding in a universe that is far more complex and mysterious than we can currently comprehend. Are we merely shadows dancing in a grand, unseen ballroom, unaware of the true nature of reality? Are there other universes hidden within the extra dimensions, teeming with life and intelligence? These are questions that may never be answered, but the very act of asking them pushes us to the limits of our imagination and expands our understanding of the universe and our place within it. The search for extra dimensions is a journey into the unknown, a quest to unravel the mysteries whispered by the fabric of space-time. It is a journey that will challenge our perceptions, expand our horizons, and ultimately transform our understanding of reality. And perhaps, just perhaps, it will lead us to a deeper connection with the universe and with each other. The universe awaits, its secrets beckoning. The dimensions are calling. Will we answer?